You know, in the high-stakes world of helicopter flight where precision and power are literally everything, some of the biggest threats are completely invisible. And I'm not talking about the obvious stuff like bad weather or pilot error, but something much more sneaky. A silent enemy that builds up inside an engine, particle by tiny particle.
All right, so let me ask you something. What do you think sand from a desert, salt spray from the ocean, and even city smog all have in common?
Well, the answer might surprise you. They can all ground a helicopter. Yep, these seemingly harmless everyday particles are the raw ingredients of a very serious problem, and that's exactly what we're going to break down right now.
Okay, so how on earth can a little bit of dust take down one of the most powerful machines ever built? Let's get right into it and take a closer look at this invisible enemy.
The technical term for this whole mess is compressor fouling. Okay, so picture a helicopter's engine. It's basically a giant, incredibly powerful air pump, right? It has to suck in huge amounts of air to create lift. But what happens when that air is dirty? Well, all that gunk, the sand, the salt, the pollution, it starts sticking to the super fast spinning blades inside the compressor. And here's the kicker. It actually changes their perfectly engineered shape. That buildup, that is fouling. And believe me, that's where all the trouble starts.
So you might be thinking, okay, a little bit of dirt. What's the big deal? Well, that's the million-dollar question. And it brings us right to our next section, how this stuff literally chokes an engine.
And honestly, there's a perfect analogy for this. If you think of the compressor as the engine's heart, but instead of blood, it's pumping air, then fouling is pretty much exactly like cholesterol clogging up your arteries. You know, at first it might not seem like a big deal, but it doesn't take long at all for that blockage to start starving the engine of the one thing it needs to survive: air.
And what happens next is this absolutely devastating domino effect. So first, that debris builds up, one tiny layer at a time. Right away, that restricts the airflow. Then, because less air is getting through, the compressor just can't build up the pressure it needs to do its job. And the final domino? The engine's power just plummets. It's this super fast chain reaction that can end in total failure. So check this out. This image gives us a peek inside a healthy T700 GE engine compressor. And yeah, this is the same kind of engine that powers a Black Hawk helicopter. See how the pressure, all those colors from blue to red, builds up really smoothly and gets super intense there at the end? That's what you want to see. Now just imagine fouling as a blockage somewhere in that flow. It creates a chokehold right where that pressure needs to be at its absolute peak. It's literally suffocating the engine.
Okay, so if this is so obviously dangerous, why don't we just, I don't know, detect it and clean it out? Well, that's the real problem, isn't it? And that brings us to the central challenge here.
See, spotting this fouling stuff early is way harder than it sounds, and for a few big reasons. First off, you can't just go around breaking multi-million-dollar engines just for research, right? So there's a serious lack of data on what these engines look like when they're actually deteriorating. Plus, most of the research out there is on these huge industrial turbines. They're a totally different beast from the compact, high-performance engines you find in a helicopter. Then you throw in constantly changing flight conditions and these newer, super complex variable-speed engines, and yeah, you've got yourself a massive diagnostic headache.
But of course, that's where some brilliant new research comes in to tackle this problem. So let's talk about the solution, a brand new diagnostic model.
Okay, this is where things get really interesting, because we're talking about a fundamental shift in how to even approach this problem. See, the old way of doing things is reactive. You look at tons of data from past failures and try to spot a pattern. But what if you don't have that data to begin with? This new method, though, it's proactive. It creates what's called a digital twin of the engine. Think of it like a perfect virtual blueprint. Then it compares the real engine's live data against that perfect blueprint in real time. So it's not looking for old problems it already knows about. It's looking for any tiny little thing that's different from perfection as it's happening.
And this quote from the researchers, Bazmi and Rahimi, really nails what their innovation is all about. Their goal was to create a method that needed less data to work, while actually being more accurate. I mean, that's the dream, right? It's all about working smarter, not just drowning in information.
So the big question is, did it actually work? Well, the researchers put their new model through a serious virtual stress test, and that's what we're going to look at now.
And they didn't mess around. They tested it on the T700 GE engine. You know, the iconic workhorse that powers the Black Hawk helicopter. So yeah, this grounds the research in a very real-world, very high-stakes scenario.
So this led them to the critical question. Just how much does this fouling stuff really mess with performance, especially during the tough moments, like hovering or climbing at high speed?
And get this, the results really show just how fine the line is between okay and catastrophic. This table breaks down the impact on a hovering helicopter, which, by the way, is one of the most power-hungry things a helicopter can do. Okay, look at this. A low level of fouling, we're talking just a 1% change in airflow, already causes a 3% power loss. But check out what happens when it hits a medium level. That's only a 2% drop in airflow. The result isn't just a little more power loss. The engine chokes. It's game over. Complete failure. That is a terrifyingly thin margin between flying and falling.
So, the all-important question, could the new model see this coming? And the answer is a resounding yes. The model hit an average accuracy of 88% in spotting these dangerous faults. That's an incredibly powerful result. It means the system can reliably flag that tiny, critical change before it turns into a disaster.
So you see, this is so much more than just some interesting academic paper. In our final section, let's zoom out and look at the big picture. What this really means for the future of flight.
So why does all this matter? Well, first, and most importantly, early detection prevents catastrophic failures. It saves lives. Simple as that. But it's also about smarter maintenance. You're fixing problems before they become huge, which saves a ton of time and money. And hey, cleaner engines are more efficient engines. They burn less fuel. Ultimately, this whole approach paves the way for a new generation of smart health monitoring, not just for helicopters, but for all kinds of complex machines.
And that kind of leaves us with one final thought to chew on. The core idea here was actually pretty elegant, right? Just compare messy reality to a perfect design to find a hidden danger. So it makes you wonder, what other invisible problems out there? In engineering, maybe medicine, even finance? What could we solve if we just started looking for that tiny, crucial difference between how things should be and how they actually are?